Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about macrostates, microstates and counting of the microstates. In the process, we will come across the Bose-Einstein and Fermi-Dirac statistics, and we will get a strategy to count the microstates that we are talking about. In the previous lecture, you remember that we discussed about the concept where a system of n molecules with energy E can be described in this manner, that they are having the energy spread over a series of quantized energy levels starting from epsilon 0 dash to epsilon 1 dash and so on, and the different energy levels can have corresponding statistical weights G naught, G 1 etc., and that came basically from the concept that one particular energy state may not be confined to one particular energy level, may not be confining to one particular energy state alone. There may be multiple states supported by the same energy level. At a certain time instant, you see that the number of molecules are distributed over the different energy levels starting from n0 to n1 spreading to nj say, and that constitutes a specific macrostates. And in the next time instant, the things may change, as we have noticed earlier that due to continuous molecular collisions, the population distributions keep changing and it may go to a different macrostate. But if you notice this event happening over a sizable period of time, then we find that most probable macrostate is something that we come across. That means, there is one particular macrostate which happens over and over again at a much higher frequency than any other macrostate, and that occurs when the system is in thermodynamic equilibrium. And the problem of finding the population distribution basically boils down to saying that we have a total number of particles n which are indistinguishable spread over j levels of quantized energy, and the total energy of the system is given by an expression like this, where the energy level of each one of those quantized states is weighted by the number of particles which are lying at that energy level. And in order to find the population distribution, we need to discuss about the microstate. And in order to go to the discussion of microstate, we have to recall this structure, that the discrete energy levels look like this. Corresponding to each level, there is a statistical weight or degeneracy, and we have to put these things together to define a microstate. So, let us now have a look at how a microstate may be appearing and what are the parameters which defines the microstate. And before we go on further, let us schematically represent some of these facts. Here we schematically represent the different macrostates that occur over a few time instants. So, you have defined the energy levels starting from the lowermost and going upwards to the highest. You have defined the statistical weights or the degeneracies, and then based on that you are defining some macrostates. That means, basically you are talking about a population distribution. Which would give rise to this relation. So, when you sum them up one by one, going to the highest level, you end up getting n number of molecules or particles for each one of the macrostates that you are looking at. However, if you look at some specific energy levels, you see that the number of particles which are there at a given energy level does change with time. So, at the bottommost level you see the population changes from 3 to 2, in the next level from 2 to 3 and so on. However, each one of them are going to maintain the same constant here in terms of the total number. Let us consider the macrostate 1 at the time t1. So, keep note of this distribution, because we are going to do a little more work on that, and we are now actually going into microstates which would emerge from that macrostate, and the microstates also emerge because of the degeneracies available at each one of the energy levels, and because of the continuous molecular collisions. All this is happening simultaneously. So, here again you have the energy levels, you have the number of particles, if you wish to call molecules, at each energy level. This is the statistical weight or degeneracy that is associated with each one of those quantized levels, and these degeneracies are going to be indicated in the form of boxes or containers. So, what do they contain? They contain the particles of the molecules. So, let us say here you have three molecules and you have 5 containers to fill them in. 5 containers comes from the fact that the degeneracy level is 5. So, you have the choice to fill in one each into 3 different containers, and this is how it fills in this particular microstate. So, the microstate is basically looking at the micro management of filling the containers with molecules. So, this gives the details within the thermodynamic system at a more microscopic level, taking into account the degeneracy. So, the degeneracy level here at this energy level is 6, which means 6 containers, 6 boxes, while you just need to fill 2 and you choose to fill them this way. Every time notice that we are filling one box with one molecule or one particle. We are not putting more than one into a particular box or container. Here again 4 particles, 6 boxes, 3 particles, 5 boxes. So, this distribution of how you fill in those molecules or particles into the available degenerate states is what gives you the microstate 1. If you look at the next instant, you may see that the same macrostate is retained, but the microstate within such a macrostate also gives rise to a new one here. So, you continue with 3 particles, 5 containers, but now you see they have been filled in a different way. 2 particles into 6, 4 particles into 6, 3 into 5, and therefore, due to the difference in distribution, microstate 1 and microstate 2 for macrostate 1. This is a zoomed view where you can look at the filling more closely. As is indicated, these are the different energy states for the same energy level. That means, these containers are all at the same energy level, but they correspond to different energy states. The same is the picture here in this case. Now, we have drawn a microstate 3 and you will see a difference over here. you see several boxes being filled with multiple molecules. So, in this microstate 3, which is again for the same macrostate 1 at T 1, how do you know that? If you look at this population distribution, then you would know better. 3, 2, 4, 3. So, if you go back, you will see it here 3, 2, 4, 3. That is what we have chosen over here. However, there is a difference compared to microstate 1 and 2, as was shown before, and in this microstate more than one particle can fill a degenerate state, which is a significant change over what we were showing in microstates 1 and 2. Now, is this a random thing that we can do? We can either fill them with more than one or just choose to fill them with one at a time? No, it is not arbitrary. It depends on the kind of molecule or atom that we are handling. The ones with even number of elementary particles, and let us call them as bosons, they can populate the degenerate states in such a manner that more than one particle can occupy a particular degenerate state. This was what was shown in microstate 3. So, they can populate the degenerate states in such a manner that more than one particle, which is a molecule or an atom, can occupy a particular degenerate state, and that is why you saw some of the containers containing multiple atoms or molecules. So, these kind of atoms or molecules, they follow the Bose-Einstein statistics, and thereby they are called by the name bosons, which carries portions of both the scientists' names who proposed this statistics. Molecules and atoms with an odd number of elementary particles, we will call them fermions, can populate the degenerate states in such a manner that only one particle can occupy a particular degenerate state. This is what was shown in microstate 1 and 2, and they follow what is called as Fermi-Dirac statistics. They are called as fermions. Therefore, you now understand the microstate 1 and 2 were drawn in line with Fermi-Dirac statistics, while the microstate 3 was drawn in line with Bose-Einstein statistics. For both fermions and bosons, the microstates are of course continuously changing because of the molecular collisions, and it is an assumption of statistical thermodynamics that each microstate can occur with equal probability. The constant change occurs due to molecular collisions. There is one particular macrostate that has the maximum number of microstates, and thus it becomes the most probable macrostate. So, there is a connection with the maximum number of microstates that can occur for a particular macrostate, which makes it the most probable one. Therefore, the macrostates and the microstates are inherently connected with each other. The most probable macrostate will occur maximum number of times, because it has the maximum number of microstates possible. And the constituent microstates, they carry the detailed information of the distribution of atoms, molecules over the different available degenerate states, which we have shown in the microstates 1, 2 and 3 that we have sketched. The most probable macrostate will occur maximum number of times over a given time span, and hence the corresponding microstates will be maximum in number. So, this is basically one way of explaining the statement which was made earlier. If you were to plot all this through a simple sketch and show that the message that we are trying to convey is something like this, that there are a large number of macro states that we can come across when we are looking at the thermodynamic system over a period of time. However, we find that there is one particular macro state which seems to repeat at a much higher frequency compared to the other macro states. And then we will see correspondingly it should be having the largest number of micro states as well, and that is why it occurs so much more frequently than the others. And that is essentially the connection between the most frequently occurring macro state and the largest number of micro states that it contains, which is basically shown through a plot like this. And the number of micro states is going to be denoted by capital W. If we were to count the number of micro states for a given macro state, then we need to represent this statistics in a suitable manner. The counting of micro states has to be done based on the following considerations. For bosons, the number of molecules or atoms that can be in a degenerate state is basically unlimited, which means a container or a box representing degeneracy would be able to contain as many number of atoms or molecules that lie at that particular energy level. There is no limitation. So, that is what is mentioned in the next statement, that is subject to the constraint that the above number which you are going to fill into a particular container should satisfy this condition, that it has to be less than equal to Nj, Nj being the number of molecules or atoms at the jth quantized energy level corresponding to the macro state that we are looking at. So, it cannot exceed Nj anyway, but it can accommodate all of them if needed. So, that is how the Bose-Einstein statistics functions for bosons, while for fermions, which is governed by Fermi-Dirac statistics, only one molecule or atom can be accommodated in a degenerate state at any given time instant. So, this rule of the game has to be followed when we formulate the counting strategy for the number of microstates. Let us look at Bose-Einstein statistics first. We will consider one energy level epsilon j dash alone to keep things simple in the beginning, and then we will try to extend the picture to other energy levels too, accounting for all the discrete quantized energy levels. Let us suppose that this particular energy level epsilon j dash has Gj degenerate states and Nj molecules. We will consider the degenerate states as containers which can hold the molecules. This picture has been emphasized many times already. So, I hope you have got a clear understanding of the concept of why we refer to them as containers or boxes. The containers will be put next to each other, sharing the partitions. So, it is like a set of boxes which are lying adjacent to each other with the partitions in between which are adjustable. You can take out one partition from anywhere, put it elsewhere and alter their locations. You can put as many molecules into one container, and therefore, there is no constraint in how many you fill into one box. There is enough space. Molecules will be indicated by a cross sign that we have been doing in the other sketches as well, and the partition by vertical bars. This is something that we have not done very explicitly, in the sense that the partitions would be shared, because in the previous pictures, if you remember, when we were drawing them, we had indicated them as individual boxes or containers. They did not seem to have partitions which were shared, but here when we work out the statistics, we would put them adjacent to each other with shared partitions. You will very soon realize why that is done, because working out the statistics then becomes very easy. So, now how can we represent the picture? We can represent it this way. So, 1, 2, 3, 4 up to Gj basically represents all the degenerate states which are possible for epsilon j dash energy level, and you have the Nj molecules distributed over those Gj degenerate states, giving you one possible microstate. And you can see that there are several degenerate states where more than one molecule has been accommodated. To name 1 and 3 are two of those degenerate states. And overall this gives you the distribution of Nj number of molecules over all these degenerate states. For example, the degenerate state 4 does not contain any molecule, and therefore it is left blank. Now, if you look at it from the statistics point of view, the number of permutations that you can perform between the symbols x and the vertical bar is given by this expression factorial Nj plus Gj minus 1. Now, we have to understand why we have written this expression. First of all, Nj is because of the number of crosses that we have, and Gj minus 1 must be because of the partitions, but since there are Gj containers, why should we write Gj minus 1? Because if you count the partitions, there will be one less than the number of containers. Therefore, Gj minus 1. So, this comes from the vertical bars that we have kept for the partitions, and factorial of that expression will give you the number of permutations between the symbols. So, we are treating the entities as symbols, and that is where having shared partitions helps us to treat them as symbols which are permuted. The partition are however indistinguishable from one another, therefore, they have been counted too many times as though they are distinguishable. Therefore, we have a much higher count than we actually should have in terms of the distribution, the population distribution within the degenerate states. The Gj minus 1 number of partitions can be permuted in factorial Gj minus 1 different ways. So, we have counted Gj minus 1 factorial times more than we really needed to do, that is as far as the indistinguishability of the partitions is concerned. Similar is the case with the molecules that we have filled in. They are also indistinguishable from one another. Therefore, they can be permuted in Nj factorial different ways without creating a new picture of the distribution of the molecules in the containers. Therefore, we need to take into account these factorial Nj times more permutations that we have considered, assuming that as though the molecules are distinguishable. To take into account both of these factors, we divide the original expression factorial Nj plus Gj minus 1 by factorial Gj minus 1 and factorial Nj, which are accounting for the repetitions. So, this gives you finally an expression for the number of permutations between the molecules and the partitions, which give you the number of possible microstates for one particular energy level epsilon j dash. Now, we have considered only one energy level with population Nj. However, we have to repeat it for all the other energy levels which comprise the entire set of molecule distribution, giving you the macrostate. Therefore, if you want to go to the macrostate picture, the total number of microstates which are involved there, which we call as W, capital W, would have to be represented by this expression pi, which runs over J, comprising of this expression for each discrete energy level. And this is of course applicable for bosons, following the rule which we have obeyed when populating the different degenerate states for a particular energy level. It is evident that as you work out this W expression, it will account for all the number of particles which populate the different energy levels starting from 0 to J, and W is called as the thermodynamic probability. It is a measure of disorder of the thermodynamic system. If you now go into Fermi-Dirac statistics, you recall the rule that for fermions, since not more than one molecule can populate a particular degenerate state, the constraint is that you must have the number of boxes or containers which are greater than or equal to Nj, without which you cannot abide by the rule that not more than one molecule can populate a particular degenerate state. The number of ways Nj molecules can be distributed over Gj containers with one or less than one molecule per container is given by this expression, which you can see over here. It is Gj times Gj minus 1 times Gj minus 2 and so on. It goes up to Gj minus Nj minus 1. So, what is the rationale behind this expression? You can say that when you are filling the first molecule out of the Nj that you need to fill, you have Gj number of boxes or containers available to you at that point. So, you can fill the first molecule in Gj number of ways. Once that is filled, you are now left with Gj minus 1 number of containers, and therefore, the second molecule can be filled that many times in that many ways, followed by the third one and so on till you reach the Njth molecule. Since for the second molecule you see that it is not Gj minus 2, but rather Gj minus 1. So, it is reduced by 1. Therefore, Njth molecule will be reduced by 1, and therefore, this count will be Gj minus Nj minus 1, not Nj alone, which finally gives you factorial Gj by factorial Gj minus Nj. Again, remember that the Nj molecules are not distinguishable from one another, and therefore, they can be permuted in factorial Nj number of ways, and all of those permutations will essentially give you the same picture in terms of distribution of molecules in the Gj containers. Therefore, you just need to take one out of those representative pictures, and in this manner the logic would be that you divide the expression that you had in the previous page here by factorial Nj, and therefore, the final expression comes to this. That is all that you need to do over here. There is no other computation involved. You just need to extend this expression now to all the energy levels. So, by considering all the energy levels, we get the total number of microstates for a given macrostate for the fermions. That is given by the expression W, and as you can notice here as well, you have a pi expression, which means this expression is going to be in a product form applied for all the J levels of energy that we are talking about, taking the different Nj values at each discrete quantized energy level. Thereby, again W will also become over here a function of N0, N1, etc. up to Nj. So, let us summarize saying that in this lecture we discussed about macrostates and microstates at length. We looked at Bose-Einstein and Fermi-Dirac statistics, and we learned to count the microstates. Thank you.